Hey, good morning, guys. So
Hey,
we're
what's up,
back.
Dave?
What's going on, DeMarco? What's up, guys? We are starting back today with a very, very exciting chapter, which is chapter 9, spanning true protocol concepts. Guys, I'm purposely going to take my time and send you guys resources on this one. This is one of my um, favorite theories, favorite subjects within routing and switching. Um, in my opinion, spanning tree is a precursor for understanding routing protocols because you have to deal with timers, you have to deal with a lot of theory, and it takes some practical use to getting used to. Okay, so with that being said, let's go ahead and get started. Okay, so we left off on we were speaking about some of the fundamentals about what what it looks like in a practical sense of what spanning tree does, right? We spoke about why we need spanning tree, right? We talked about, you know, what the problems spanning trees bring, right? If it didn't exist within a topology that had redundant links, it brings broadcast storms. What are broadcast storms? Broadcast storms are um, the the um, the topology of which, whenever a switch is forwarding a frame, right, on redundant links, it's consuming significant parts of those links because there's never a stopping point. Okay, so it's just going on in circle and circle and circle, right? Here, let's go ahead and go back to the last example that I showed you guys in the last class, right? Without spanning tree, okay, broadcast storm happens, right? It goes on and on and on, right? What else do we have happen whenever we don't have spanning tree that exists within our local area networks that have redundant links, right? We have MAC table instability, right? The continual updating of a switch's MAC address table with incorrect entries, right? In reaction to looping frames, resulting in frames being sent to the wrong location. Okay, we spoke about that before. All right. Last but not least, without spanning tree existing within the topology, we also suffer from multiple frame transmission. Okay. That's one of the other side effects of looping frames, in which multiple copies of one frame are delivered to the intended host, confusing the host. Okay. All right. So let's talk about what spanning tree does. Okay. And let's go from there. All right. So let's talk about it. Right. So spanning tree, right? What does it do? Right. It prevents loops by placing each switch port in either a forwarding state or a blocking state. Okay. Interfaces in the forwarding state act as normal, right? What does that mean, normal, right? In terms of spanning tree, it's either forwarding and receiving frames. Okay. Now, the opposite of that, right? If the interface is in a blocking state, okay, they do not process any frames except for spanning tree and rapid spanning tree messages, right? And of course, some other control plane messages like dynamic trunking protocol, anything that has to do with engaging the control plane to make a change, okay? Or to just inform, right, the control plane of something. All right. Um, Interfaces that do not block, do not forward user frames, do not learn MAC addresses of receive frames. They do not process receive user frames either. So that blocked port, okay, that blocked port is not even learning MAC addresses, okay? Not learning MAC addresses, not receiving frames, what have you. And again, we call it frame because the protocol data unit at layer two, the term for it is frames, okay? So I will never call it a packet. I don't need to call it a packet at layer two. We will always call it a frame, okay? All right. So let's keep going, right? So how spanning tree works, right, is it creates an algorithm, right? And that algorithm creates a spanning tree of interfaces that forward frames, right? It's a tree structure, right? And so that tree structure, it's a structure of forwarding interfaces that creates a single path to and from each Ethernet link, just like you can trace a single path in a living, growing tree from the base of the tree to each leaf. I want you guys to understand that. That is, at a high level, that is the core of spanning tree. It creates an algorithm, right? And that algorithm, that purpose is to create a tree structure of forwarding interfaces that creates a single path to and from each Ethernet link, just like you can trace a single path in a living, growing tree from the base of the tree to each leaf. Okay? All right? 1 second. I want to show you a diagram. Okay, because I spoke about this in the last session, but I didn't go much in depth because I didn't want to overload you guys. Okay, so remember what I just said, right? It's create that algorithm is a forwarding interfaces creates a single path to and from each Ethernet link. So if I'm on switch 3, I have a single path to switch 1. If I'm on switch 3, again, I have a single path to switch 2, right? I have a backup link, I have a redundant link to switch to, right? But in terms of spanning tree, so we don't engage in those 3 errors that happen whenever a spanning tree doesn't exist in the environment, right? Broadcast storm, MAC address instability, MAC address table instability, and multiple frame transmission, right? We're going to block that, right? Because the tree structure of forwarding interfaces creates a single path to and from each Ethernet link. Okay? Just like you can trace a single path in a living, growing tree. Okay? Right? This is just at a high level, right? At a low level, this process is called the spanning tree algorithm, STA. Okay? And again, in this algorithm, right, it's choosing which interfaces should be placed in a forwarding state, right? And for the interfaces that are not chosen to be in a forwarding state, okay, they're placed in a blocking state. Okay, so that FTA, the spanning tree algorithm, it's simply right. It's gonna go ahead and choose which interfaces should forward, right, and to which interfaces should be left in a blocking state. Okay, now there's always with every algorithm there is a method to the madness, right? There is a criteria that needs to be met for conditions to be met for things to satisfy, right? Let's talk about this. Okay, so spanning tree uses 3 criteria, right? When it wants to choose to either put an interface in a forwarding state. Okay, all right. So spanning tree, right? First things first is going to go within any spanning tree redundant link setup, right? It's always going to elect its root switch first, right? Root switch, another term for it is root bridge. Okay. Um, it's always going to choose the root switch first, right? It puts the root switch that is chosen within that topology is going to put all of its working interfaces on the root switch in a forwarding state. Okay. Next, right? Each non-root switch calculates the least cost path between itself and the root switch. Okay. On both of its links. Okay, based on the spanning tree interface cost. So again, what's more to come is that each interface has a cost, whether it be regular Ethernet interface, whether it be a fast Ethernet interface, whether it be a gigabit Ethernet interface or more, right? Each type of interface within spanning tree has a cost. Okay. The switch port that begins that least cost path is its root port. Okay. So that port, right? If we're talking about spanning tree, right, and we have redundant links, whichever port has the least cost to reach the root is going to become the root port. Okay. right? And that path, right? That path, right? That interface that has the least cost, right? Is called the root cause, right? So if the root cause is lower, okay, that interface on the switch is going to be chosen to become the root port, okay? Last but not least, in modern Ethernet, right, that uses switches, each physical link connects two devices only. With two switches on a link, the switch with the lowest root cause becomes the designated switch. And in its port connected to that link is the designated port, right, on that link. Okay, I know that was a lot, but once I show you the diagram, it'll make and we explain it, we go through it, it'll make sense. Okay, all right. So let's go ahead and erase this, right? Now, um, just a note, right? A root switch places all interfaces, right, into a forwarding state because each port on the root switch always wins its designated port election, right? And again, like I said, we're going to talk about designated port, um, elections and what have you, and criteria in a second. However, it is easier to just remember for the exam, right, and of course for your career, that if it's a root switch, all the root switches interfaces will always be in a forwarding state, right? And they will always be forwarding frames. Okay. Okay. So let's talk about spanning trees reasons for forwarding or blocking, right? Okay. So, and again, this is the key topic, so let's try to pay attention. All right. So characterization of port. All the root switches ports, right? The state of it, right, is forwarding, right? The description, the root switch is always a designated switch on all connected segments, okay? It's designated to forward frames, okay? So each non-root switch's root port, okay? It's in a forwarding state, right? The port through which the switch has the least cost to reach the root switch, lowest root cost, okay? All right. Each land's designated port, right? It's in a forwarding state, right? The switch forwarding the hello on to, and when I say hello, it's the hello BPDU, right? It's a hello message to other switches to say, hey, here is my bridge ID, right? And here's my information. We'll talk about that in the future, right? So the switch forwarding the hello onto the segment with the lowest root cost is the designated switch for that segment. Okay. So again, the designated port, right? It's in, and of course, the designated switch, because now I brought up that term, that is in terms of a segment or a link between two switches, right? And these two switches are not the root switch. Okay. This is what this means. Okay. So, and last but not least, all other working ports that are not the top three are placed in a blocking state. Right? The port is not used for forwarding user frames, nor are any frames received on these interfaces considering for forwarding. Okay? All right. So let's go ahead and I think we should read this together, right? So spanning tree, right, should not use non-working interfaces in the working spanning tree topology. To remove all non-working interfaces from consideration, that is, all that are not in a connected up-up interface state. Okay, so layer one, layer two, learned about that before. Spanning tree assigns non-working ports with the disabled port role. Okay, just a different type of role, right? The spanning tree does not consider these ports as potential root ports or designated ports, right? Spanning tree just also places these ports into a disabled state, okay? Just like blocking, all right? So we're getting into spanning tree, we're getting into, how does it work, what have you, and some of the particulars, but we need to get a little bit deeper, right? We talked about, hey, there's an election process that happens. We've talked about there's a cost on each link, right? But how does that happen, right? We whenever we going through the table, right, we saw a term, right, that sparked my interest. It's a hello. Okay. So any of you guys in here that worked with firewalls, that works with routing protocols, right? A hello message, right? A hello frame, hello packet is very important to any type of theory that's used within routing and switching. Okay. It communicates a state, right, in regards to the specific technology, right? OSPF, if we're sending hellos, right? It's a purpose, right, to influence the routing strategy, right, and the routing domain, right? Same for spanning tree. If we're sending a hello, we are trying to update, keep updated, right, um, or influence, right, the spanning tree algorithm. Okay, so you have to understand what a hello is. Okay, so let's talk about what a hello is, right? And I wanted to show this excerpt so we can all look at this together. We can break it down. I actually want you guys to unmute, right? Because after we're done, I want to stop here and give you guys time to ask questions, right? So let's talk about it, right? So before we can build that spanning tree topology, because I want you guys to be able to do this with a piece of paper, right? And a pencil, right? That's how I know you guys know spanning tree, right? One of the core things for the spanning tree algorithm to be built is we need the bridge ID and we need a hello BPDU, right? BPDU stands for Bridge Protocol Data Unit, okay? And those are the messages that are being sent, no matter if the interface is in a forwarding or a blocking state, between switches that are operating within spanning tree, okay? So the spanning tree algorithm, right? It begins with an election of one switch to be the root switch. We went over that, right? And of course, I want you guys to understand this election process, right? And we need to talk about these messages that are being sent to and from each switch, right? So, what they call these messages, right? They call them, bridge protocol data units, right? But what's within them, right, is information about your switch, right? Um, what you're going to have in there is information about your MAC address and a priority, right? What that information is called is your bridge ID. Okay. What is a bridge ID? A bridge ID is an 8-byte value unique to each switch. The bridge ID consists of a 2-byte priority field and a 6-byte system ID, with the system ID being based on a universal burned in MAC address in each switch. Okay. All right. So that 6-byte system ID, right? As you want to think about that, has the MAC address for the entire switch, not for the specific interface, for the entire switch. Okay. The other part of that bridge ID is a 2-byte priority field. Okay. All right. So spanning tree defines messages called BPDUs, all right? Also called configuration BPDUs, right? Which switches use to exchange information with each other. The most common BPDU, called a hello BPDU, right? You guys will know this for the exam, lists many details, including the sending switch's bridge ID. This is very important, right? By listing its own unique bridge ID, switches can tell which switch sent the hello BPDU. Okay. So if you ever have packet tracer, Wireshark, right, or a protocol analyzer that can look at data that's traversing on the wire, right, on an Ethernet or fiber or what have you, any type of physical medium, you can see, right, you will see some bridge protocol data units that traverse the wire if you're capturing that data between switches. Okay. So let's go ahead and go over some of the fields within a Hello BPD. So we're going to see the root bridge ID, right? The bridge ID of the switch that the sender of this hello currently believes to be the root switch, right? We're also going to see the sender bridges ID, right? The bridge ID of the switch sending this hello BPDU, right? The sender's root calls, right? Right? The cost between this switch and the current root. I want you guys to remember these top three because I'm going to confuse you in a little bit, right? And of course, last but not least, and this is what I mean as far as a precursor for routing protocols. Timer values on the root switch includes the hello timer, max age timer, and the forward delay timer. Okay? All right. We'll talk about the timers way later. The first three, I want you guys to just burn in your mind. Okay? Okay. We got 7 minutes left, but we're good on time. Okay. Now we're going to get really in the details of it. Okay. I know this is a lot. We have to go through this. Okay. So electing a root switch. Okay. Switches elect a root switch based on the bridge ID in the BPDUs. Okay. The root switch is the switch with the lowest numeric value for the bridge ID. Okay. Because the two-part, right, the priority and of course the burned in MAC address, right? The two-part bridge ID starts with the priority value. Okay? So if I'm the switch, right? If I'm the switch and DeMarco's the other switch, remember there's two parts of the bridge protocol data unit, right? There is the priority and the burned in MAC address. We're looking what the switches are in the CPUs, right? The control plane is always going to look when processing these BPDUs is the priority, right? That's the value we're looking at first. Okay. Essentially, the switch with the lowest priority becomes the root. For example, right? If DeMarco's switch has a priority of 4096, and my switch has a priority of 8192, right? The Marco switch becomes the root switch, right? Okay. It is first going to look at the switch with the lowest priority in regards to exiting a root switch, right? Now that can't be the entire criteria, right? We're always going to have, right? It is possible that nobody's changed the value for the priority. So we may have a tie. We need a tiebreaker, right? If a tie occurs based on the priority portion of the bridge ID, the switch with the lowest MAC address, right, of the bridge ID is the root. No other tiebreaker should be needed, right? Why? Why shouldn't they be needed? It's because each device on this planet, right, that's involved within networking, right, has its own MAC address burned in that's universally unique to that device. Okay. All right. The first part of a MAC address, right? If I'm over explaining, I'm sorry, guys. The first part of the MAC address has a OUI, right? Organizational Universal Identifier, right? That identifies the company where it comes from, right? So um, Dell, maybe Intel or something, whatever, right? The last part is unique, right, to that device. Okay. All right. So if me and DeMarco has the same priority, if he has a lower MAC address than I do, right, then he's going to win, right? So let's go ahead and break that down because I want to make sure that makes sense, right? So if the priorities tie and one switch uses the MAC address of 0200.0000.000 has part of the bridge ID, and the other one uses 08111.1111.1111, right? The first switch, MAC, right? That MAC address becomes the root switch. Okay. Why does it become the root switch? Right. So what we're doing is we're going to compare each bit, right? Each decimal value, right? Starting, right? Okay. So I see zero. Zero is the same. Excellent. I see eight here and I see two. This is the switch with the lowest burned in MAC address. This is going to win the tie. You guys need to know this. I want you guys to be able to converge, do STP convergence with your hands. Okay? I hope this makes sense. Okay? All right. Clear that. Right. Last but not least, spanning tree elects a root switch in a manner not unlike a political election. I don't know why the book put that in there. The process begins with all switches claiming to be the root. I'll say it again. The process begins with all switches claiming to be the root by sending hello BPDUs, listing their own bridge ID as the root bridge ID. Okay? If a switch hears a hello that lists a better lower bridge ID, that switch stops advertising itself as root, right? The switch that we were talking about, and starts forwarding the superior hello, right? So if I'm not connected to DeMarco, right? Let's take a pause right here. I just wanted to make sense. If I'm not connected to DeMarco, out of the box, my switch, right, is going to think that it is the root switch. Okay? It's going to be sending BPDUs, right, out to the ether, right, as long as the interface is up, right, and I'm connected, it's going to be saying, hey, I am the root switch. Okay? Okay? In the root, in the root bridge ID section, if I'm doing a Wireshark capture, I'm seeing that. As soon as I connect to DeMarco, right? We're going to, of course, I'm going to constantly send, based on the hello timer, I'm going to constantly send BPDUs, right? I'm able to receive BPDUs as well. If I receive a BPDU and DeMarco's, right, hello BPDU has all the information, right? Root, root bridge ID, which of course is his, right? Because we both think that we're both have the lowest bridge ID, right? And it has, of course, our own bridge ID, which of course is the same as the root at the time. As soon as we connect, if we see, we compare, because we also can receive hellos, right? As long as we're in a forwarding state, we receive that and we say, oh, hey, DeMarco, I received your BPDU. Sorry, guys, I can't talk this morning. And your priority, right, is lower than mine, right? You have a better, you have a better, BPDU, right? Better bridge ID than I do. Okay, excellent. I'm going to go ahead and send you a frame that has you listed, right? Has the root bridge for this connection. Okay. You are the superior switch. Okay. Now, a better hello, right? A better hello frame, a hello message, meaning that the listed root's bridge ID is better, numerically lower, is called a superior hello, right? So if we're looking at a BPDU, right, and their values are lower, numerically lower, that is the superior hello, right? A worse hello, right? Meaning that the listed root's bridge ID is not as good, numerically higher, right? Is called an inferior hello. Okay. So in terms of spanning tree, lower is better, which is called a superior hello. Okay. Higher, right? A worse hello is called an inferior hello. Okay. All right. Last but not least, right? And we're going to stop here. I want everybody to take a screenshot and I'll put this in the Discord. I want you guys with your hands to be able to tell me which switch. Well, we can do it now. Everybody unmute. All right. We got time. Which switch, based on what we went over, is the root switch? Who's gonna win this election process? And we can have an open discussion. Nobody has to wait.
Uh,
Based on everything that we just went over.
Is it switch one?
Yeah, that's what I was
I was
gonna
thinking, I
say.
was looking at Switch One.
Switch one.
Switch one has the lowest MAC
Yeah, I was
address.
definitely looking at Switch One.
And its cost is the same?
Okay. So, Donovan,
Yeah.
talk
Yes.
to me. Talk to me. So, why do you believe, based on what you just learned, that switch one is going to be the root switch?
Okay, so I noticed at first we had three conflicts with like the priority,
Hmm.
and then I found the lowest MAC address
Good.
from those conflicts, which was switch one.
Okay, give me more detail. What are the conflicts that you saw?
Um,
You're
the
almost you're almost there, by the way.
The BID and the
Okay.
root BID is the same.
Okay.
Um,
Okay. Hold on. Stop. Why is it the same whenever it sends out? Isn't that default behavior?
yeah, when it comes
Awesome.
on, yeah.
Awesome. Okay. Keep going.
And I had to find something that's like the lowest, it goes by the lowest MAC address at that point,
Hmm.
um, which switch is going to take precedence. So switch one.
Hmm. Okay. Tell me. So you're good. You're on the right path, but I want you to fully explain it. Talk to
Okay.
me. Talk to me, right? Because as soon as we cut these switches on, right? They're able to send, and what the control plane is going to do is send those bridge protocol data units, right? Going to send those
Mhm.
hellos, but it's also going to be able to receive hellos. What is it seeing when it receives the hellos? Tell me what it sees whenever it receives a hello on switch one and doing the comparison in regards of criteria for selecting the root switch. And my Kivia, I want you to tell me what switch one sees whenever doing the comparison of receiving a hello from switch two.
Is it called like the frames?
Mm-hmm. Tell me about what it sees whenever we're looking at the bridge ID of itself and the received bridge ID.
Um, which ID itself in the free? Is it looking for? I think you said like the eight. No, wait, hold on. Let me give me a second.
Mm-hmm. Take your time. So Don, let's do this together. You're on the right
Okay.
path, okay? All right. So switch one, right? I'm switch one.
Hmm.
Sorry, I can't write. Terrible. And DeMarco, I'm sorry, I'm not spelling your name out. I'm just call it them, right? So switch one and switch three, right? We're receiving each other's hellos, right? What the switch's job is supposed to do is to compare its own, it receives the bridge protocol data unit, it breaks it down, and it says, let me compare the values and see if their values are numerically lower than mine, because then that's going to be the superior hello. Okay. What am I comparing? I'm comparing the the bridge ID. The bridge ID consists of what? The priority and the MAC address, correct?
Yes.
So if I'm looking at the hello that I received from switch three, right? And if I'm switch one, I said, oh, what's the same?
The BID and the
The priority. This
priority.
this first part is the priority. Okay.
Oh, okay.
Okay. So that first part is the priority. Now we need to go to the tiebreaker. The tiebreaker is what? The MAC address.
MAC address. Okay.
So now I need to see what's different. What's
And
different,
The
right?
MAC address.
Okay.
It's
And where does it become different? Okay. You need to be able to identify that. It's the same right here, right? Okay.
uh,
But we're not going to focus on it being the same, right? If it's either the same or lower, we have to move on to the next decimal. Okay. 0, 0. It's the same. We got to move on. 2, 2. It's the same. We got to move on. 0, 0. We have to move on. 0, 0. We have to move on. So this first byte, we can move, right? This first octet, I apologize. We're going to go ahead and move on, right? Moving to the next octet, right? 0,
mhm.
0. Boom. Same, right? We still have the same. right? 0, 0, right? Still the
Uh-oh.
same. 0, 0, still the same. Uh-oh. Uh-oh. We got it. We got a difference. 1 and 3. Which one is lower?
Which one?
Boom. Switch one won the election because of the tiebreaker. Okay. Mike Hevia, same thing for between switch 2, right, and switch 1. Okay. And we can just do it right here, right? At what point in the bridge ID did switch 1 win?
And the second octet, because the my BID is 2 and switch 1 is 1.
Holy crap. Good stuff. Exactly, guys. I want guys to be able, and I want you guys to do some practice on your own until we come back Thursday. But I need you guys to be able to do this, to understand this. You guys can create your own switches and configure a priority on paper and give of course these switches a burned in MAC address. I want you guys to practice it if you're bored, if you're chilling. I don't know if you're listening to some SZA, whatever, right? Practice this. If you're able to do this on paper, you will pass the exam. I guarantee you. Okay? This is a very critical chapter. I need you guys to understand that. Okay? With that being said, we'll stop here and we'll continue on Thursday. Okay?
All right, Dave. Appreciate it.
Alrighty.
All right,
Thanks.
guys. Thanks,
Bye,
guys.
Later.
y'all.